This is a presentation for Mamba-ND selective state space modeling for multidimensional data. I'm Shufan Li, the first author of this paper. State space models is a special type of model that continuously transforms a 1D sequence to another 1D sequence using the following differential equation. This can be discretized to the following difference equation using the zero-order Hold rule. Concretely, these formulations provide an alternative way for sequence modeling that is different from transformers, the de facto standard. Typical state space models such as S4 follows linear time invariance, also known as LTI, which means that we can convert the sequential operator into a 1D convolution as listed in this formula. In this way, we can compute the full sequence in parallel. These models can also be easily extended to 2D and 3D data by constructing a 2D or 3D convolution kernel through the outer product of 1D kernels. Selective state space models, also known as Mamba, breaks the LTI by making delta B and C in the formulation dependent on the input signal xt. Consequently, the difference equation can no longer be converted to a 1D convolution. Therefore, Mamba proposed a custom CUDA kernel using selective scan to accelerate the inference and training. However, extending it beyond 1D is not as straightforward as converting a convolution 1D to convolution 2D. To apply Mamba to multidimensional data, we must first flatten an ND array to a 1D sequence. Taking 2D array for example, there are at least 4 options listed in this image. We call these flattening options as scan ordering. For 3D data, there will be more options. Ideally, we want the model to process the input from multiple directions. This means that we need to extend the vanilla Mamba layer, also known as 1D SSM, to a version that can process a single sequence in multiple directions. In the standard 1D SSM layer shown in this graph, the sequence is only processed in sequential order. In the bidirectional SSM, the sequences are processed in 2 orders, forward and backward. In the ND-SSM, the sequence is processed in n orders. For 2D data, it is processed in 4 ordering shown in the previous slide. For 3D data, it is processed in 3 different orders. The multi-head SSM borrows from the idea of transformer, where we first split the input data into multiple heads and process each head at a separate, different direction. Alternatively, we can also choose to keep the architecture of a single layer, i.e. we keep the 1D SSM design, but we can process the sequence at different layers using a different scan ordering. We can also optionally group these layers together into blocks. Further, just as 3D attention can be factorized into a 2D attention and a 1D attention in video modeling, we can also factorize a 3D Mamba layer into a 2D layer and a 1D layer. Or we can actually factorize it into 3 1D layers. We experiment with all these design choices on ImageNet 1K classification and HMDB action recognition. It turns out that a simple approach works the best. First, we keep the 1D SSM layer untouched. Secondly, we interchange the scan ordering between layers. Our final design is shown in this graph, where we have a Mamba-ND block consists of 6 layers, each of which are simple 1D SSM layer, but they process the input sequence at a different direction. Mamba-ND achieves higher performance and less parameters compared with the state-of-the-art transformers on 4 tasks: image classification, action recognition, weather forecast, and 3D segmentation. In each of these tasks, Mamba-ND was able to outperform transformers with significantly less parameters, highlighting the efficiency of our algorithms. Even on large-scale action recognition, such as connected 400 dataset, and long video understanding, such as breakfast, Mamba-ND also outperforms transformers and previous state space models. Through the visual examination of effective receptive field, we see that our multidirectional design is crucial for the model to perceive the information across the image. Mamba-ND maintains a linear growth of compute with respect to sequence length, making it particularly friendly for scaling to the larger scale, as opposed to the quadratic complexity of self-attention in transformers. This concludes my presentation.